We're now going to talk about a very important operation involving matrices and vectors. It's matrix vector multiplication. It's not something we've seen before, but it's actually going to be used basically throughout the entire book and class from now on. It's matrix vector multiplication. So here's what it is. If I have an m by n matrix and an n vector, so that means that the matrix here, if I write it out, it's going to have m rows and n columns. Then I can multiply it by an n vector like that. And the way we denote matrix vector multiplication is just concatenation, meaning you put the two symbols next to each other. So you just say AX. Just like a lot of algebra, just put the two symbols next to each other and it means the product. In this case, it means matrix vector product. And so we'll call it, if that's that, what you get from the matrix vector product is an M vector. And its ith entry is exactly this. You go across the ith row of A and you multiply those by all the entries in X. That's if you might recognize that as an inner product, and you are right, it is an inner product, right? So let's see let's just do a quick example now just to make sure this makes sense. And it's confusing at first with all the indices flying around, and you'll get used to it. And also, right now, you haven't seen any applications of this, so it doesn't mean anything. So just consider this for the moment, kind of like the rules of chess. You don't ask, why can you do that or why can you not do that? It's just the rules for now. Okay. Let's multiply. Let's do matrix vector multiplication. Here is a 2 by 3 matrix, and here's a 3 vector. The first check is when you multiply an m by n matrix by a vector x. N, that's the second dimension of the matrix, has to match the vector dimension. And that's true here because this is 2 times 3, and that's a 3 by 1, if you like, or 3 vector. Okay? The result is going to be a 2 vector. So, and sure enough, it is. Now let's see how to get it. Well, what you do is the first entry in Y, which just happens to be 3, is you take the first row of A. This is A, this matrix here. This is A, and this is X, and that is Y. We go across the first row of X, and we multiply by the corresponding thing. Or if you like, you could say roughly we take the inner product of the first row of A and X, and that gives this. And I mean, we can even check that. It's 0 plus 2, and then plus 1, the minus 1 times minus 1, and so we get 3. Okay, and that's correct. So that's the idea. That's matrix vector multiplication. Now, we can interpret this tons of ways, right? And all of them, we're going to use every single one in the sequel. So the first is, you can express this as simply if you have the rows of A and call them B1 transpose up to BM transpose. Now B here are column vectors, right? Not row vectors. But when you transpose them, they become row vectors. So B1 transpose is the first row of A. Then you can write this. Y equals AX is, well, it's B1 transpose X, but which we now know is the inner product, right? So it's the inner product of B and X. So you could think of matrix vector multiplication as simply, it's like taking the inner product of every row of the matrix with the vector x, let's say. Okay, so you can think of a batch inner product, for example. And here's an example. If I say, what is A1's? Bold 1 is the vector with all entries 1. Then that gives you a vector, and it gives you the row sums of A, right? So, for example, if I have a matrix A is 0, 1, minus 1, 2. Then if I multiply that by 1, 1, what I get is the first one is I get 1 here, and down here I get 1, right? And this is 1 is the sum of the first row. This one is the sum of the second row, right? So when you see A1, you should be thinking, okay, that's row sums. Okay. By the way, these are kind of important because you're going to want to be thinking about rows, columns, row sums, column sums, all sorts of stuff like that. Okay. Column interpretation is also super interesting and uses a concept we've already seen. If I write y equals ax, I can think of it as y is a linear combination of the columns of A. So if A1 through AN are the columns of A, then y is literally x1 a1 plus x2 a2 plus xn an. So you can think of that. you can think of vector matrix multiplication as super compact notation for forming linear combinations of the columns of A using the coefficients given by X. Okay, so here's a super important example. It's something you just absolutely need to know. A times EJ, EJ is the jth unit vector, is the jth column of A. Okay, and so I mean, it's kind of interesting, right? You would say things like this. You would say that multiplying a matrix by EJ picks out the jth column. So let's just check that just for fun. Let's go to 0, -1, 3, 1, 0. And let's multiply that by the second unit vector. Okay? And what do we get? Well, let's just do matrix multiplication. I sort of take the inner product of this with this, and I'll do it in my head. 0, 0. Ooh, it's 0. Okay, so I get up here 0. Okay, and now in my head, I'm going to take the inner product of this with this, and I get 1. And sure enough, look what I just got. I just got the second column because this is A times E2 equals A2. Okay, so, and we're going to use this both ways. If you multiply a matrix by a unit vector, you're picking out a column. Also, sometimes we will want to, we'll go the other, the interpretation will go the other way. So, okay. Linear independence. Linear independence says that if a linear combination of a bunch of vectors is 0, the only way to do that is with the coefficients being 0. So now we can write it in matrix vector notation super compactly. We would say the columns of A are linearly independent if AX equals 0 implies A equals 0. And just to kind of put a seed in your mind, I'm going to say something more about that. We can interpret it this way. If A and X were numbers, and I walked up to you and I said, hey, AX is 0, product of two numbers is 0, then what you know is one of those two numbers is 0. Or another way to say it is this. If I say that AX is 0, and think of these as numbers now, is 0, and I tell you A is non-zero, then you could say, well, then X has to be 0, period. Okay. Or you could say things like, I can cancel A from this equation, or something like that. Okay. Now, that's what linear independence means, except it's for matrices and vectors. It says that if you have AX equals 0, we can conclude X is 0, right? So roughly speaking, we can cancel A or something from the equation. And so we can see there that linear independence can be interpreted as sort of like, of the columns can be sort of interpreted as a fancy matrix appropriate way of saying A is non-zero in the sense that it can be canceled. So, okay, that was all vague and weird, but we'll get to all those ideas later.